This video introduces a software environment for modeling spatial qualities of architecture called Descriptor. When we describe our built environments, we often use terms such as enclosed, view, or private. Spatial qualities are those common terms that may or may have not been defined explicitly. When launching the program, the user sees two windows. The left is the diagram editor. The user can sketch or open saved diagrams. The right, the language editor, for choosing or creating the analysis criteria. The simplest way to analyze diagrams is to use built-in definitions from the descriptor language shown on the left of the first page of the language editor. For example, enclosure is a common architectural quality that can be related to many other experiences such as sense of territory, privacy, or safety. The user can change the diagram as he designs, for example, adding columns, and apply the built-in definition on the fly. The darker color indicates the degree of enclosure is higher at the location, meaning if the area is colored darker, it is relatively more enclosed. The user can adjust values of the parameters for analysis which change the visualization. Imagine the user, a designer, defines private area. Let's say his first definition of private area is highly enclosed. He changed the degree of enclosure and set up the minimum and maximum values that are desirable. Descriptor allows the user to save the analysis criteria and the result of the analysis in separate files, and saves the result of the analysis of the selected value parameter for the term private. Descriptor saves the data in various types. First, the diagram, the building configuration as the coordinates of the built element. Second, the analysis criteria in the form of text. And the third, the result of the analysis as an image. Human spatial experiences may not be that simple. In descriptor environment, terms can be combined through logic operations and, or, and not. Some parameters are logically alternated. Visible and invisible are logical complements for each other. The red dot in the diagram editor indicates the viewer's location. The user moves the viewer's current location by clicking. Some qualities are dependent to the viewer's location. In this example, the invisible area, shown as pink, changes as the viewer moves. His second definition of private area is somewhat more complicated. The degree of desirable enclosure changes, and it's invisible from the entry of the building. The user adjusts the enclosed area as he imagined it to be. To construct a compound definition of private, he is exploring what he is envisioning. Then, he is making a logical compound by adding the visible area on top of the enclosed area. This is a conventional way of making a decision in constructing a definition for a spatial quality. The user can compare the history of previous analysis. In the History panel, the user can ask the program to show previously saved definitions and their criteria side by side. You've seen a simple way of using built-in definitions in descriptor environment as provided. Next part of the video will show you an advanced way to construct new terms using the language of the program. The constructed terms are based on an analysis of Christopher Alexander's A pattern language. Now, the user opens an office building floor plan diagram. First term enclosed, according to Alexander, is defined as sum of lengths of surrounding walls. The user directly types those terms in the text editor. You can see the available functions at the top of the language editor. The user sets the minimum value. Total length of surrounding walls is greater than 100. Function surrounding has two arguments, so the user inserts an additional argument and wait to see what's happening. This doesn't seem to mean much, so the user doubles the minimum value from 100 to 200. What will happen if the user changes the value again from 200 to something that's higher? If the user changes the value to 250, half of the building is not enclosed. Second term, personal, is defined as distance to the nearest wall is smaller than some number, which is arbitrary at this point. The user sets the maximum distance to the nearest wall as 30 pixel point. Function nearest and distance both have two arguments, so the user is adding that. The user is basically programming when creating a term, a model as in economics or physics. It is consistent, applicable to multiple instances, and the consequence is somehow predictable. The user decreases the maximum distance to 20. The user keeps reducing the maximum value to 15. You can see only the corners of rooms are personal, and the area gets smaller. Third term, contained, defined as the size of visual area for a location in the space. This means when the size of visual area is smaller than 10% of the size of the entire field, one might feel contained. This number is already normalized to the field size. The result seems fine, but again the user wants to check out the differences as he explores the value range. The user cut down the value to 5. That means whether one can see 5% of the field from a location. What is going to happen when the user decreasing the value? You can see some part of the hallway is not included this time. That means if standing at those spots, one will feel not contained. We can naturally think the white part of the hallway can be used as common spaces where we put coffee tables or whiteboards because the less contained area must be more accessible for internal workspace communication. This type of process, finding relationships, making inferences, negotiating value ranges, is an important aspect for a design process. The viewer is placed to calculate view field. We have this constructed term contained and another built-in term enclosed, overlapped all at the same time. This part of the demo basically shows that there are multiple ways to mix and match different kinds of terms within the descriptor environment. An underlying question of this work is how we can computationally represent spatial qualities. Descriptor provides a simple set of functions, so the qualities become describable in terms of common geometric attributes of physical elements. It also supports construction of user-defined terms. Once defined, a term can be used as an additional unit of encapsulated spatial description. That means the language itself can grow by the user.